Okay. Okay. Share my screen. All right, so let me continue from where I left off in assignment 5. And can somebody remind me the very last question I did? I think I remember doing at least one of the titration questions from number 2. I think I remember doing the A part. I don't remember if I did the B part or the C part. Can someone remind me?
I believe we're on B.
B? Okay. Oh, thank you, Miss Esperanza. Okay, all right. So somebody just confirm what you just said. All right. So let's look at the B part. Now, let me see here. In the case of the A part, we start off with 12 mils of that, 6 mils of 0.2, and well, you know what? I just realized something. So basically, A and B is very similar. The only difference is that the acid is different, and therefore the Ka value will be different. All right. So basically, you just follow the same process in the case of B, follow the same process as was done in A. All right. So I'm going to leave that for you guys to do on your own. Again, if you have any questions about that, please let me know. Let me look at the C part. Now, C part. Okay, now C part is a bit different because not only is the acid different, but the molarity of the acid is different. So I'm going to start off with the C part. Now, according to the question in the beginning, you're starting off with 12.00 mils of 0.0500 m sodium hydroxide. So what I would do is, I would start off with 12.00. I think I did this calculation already, but I'm going to do it again in any case. So what I'm calculating here is the number of moles of the sodium hydroxide, all right? So that's 12.00 mils, we convert to liters, 1 liter over 1,000 mils, and then we multiply by the molarity, which is 0.0500 moles per liter, and then we work this out. So that's going to be 12 divided by 1,000 times 0.05. So according to my calculation, this would be 6.00 times 10 to the minus 4 moles of the sodium hydroxide. Okay, so we needed that information first. So let me scroll down now to the actual question, the C part. Okay, so the next thing I would do is I would calculate the number of moles of the acid. I'm going to use HA to represent the acid. So number of moles of HA would be equal to 6.00 mils times 1 liter over 1,000 mils times, in this case, the molarity is 0.100 moles per liter. So let's see what that gives. So that's 6 divided by 1,000 times 0.1. So that would be 6.00 times 10 to the minus 4 moles, all right? So the interesting thing about this situation is that the number of moles of the acid and the base would be the same. Now, the reaction, of course, between the sodium hydroxide and the acid would be what you see here, right? So if we set up a nice table, initially we're going to have 6.00 times 10 to the minus 4 moles of the base. We're going to have the same number of moles of the acid, 6.00 times 10 to the minus 4 moles of the acid. Here, we're gonna have none of this, and we don't need to concern ourselves with the water. So basically what's gonna happen is that because these two are stoichiometrically equivalent, they'll be both completely used up. So basically, we're gonna say that the change for the sodium hydroxide is minus 6.00 times 10 to the minus 4 moles. The same will be true for the HA, 6.00 times 10 to the minus 4 moles. And then for the sodium butanoate, that will be plus, the change will be plus 6.00 times 10 to the minus 4 moles. All right? So at the end of the reaction, you're gonna have none of this, and the only thing that will remain would be 6.00 times 10 to the minus 4 moles of the sodium salt of butanoic acid. Okay, I'm gonna need some space. So what I'm gonna do is erase up here. Okay, so what we have calculated so far is the number of moles of sodium butanoate that will be present. And by the way, this here, where the amount of sodium hydroxide and the amount of the acid is stoichiometrically equivalent, we call that the equivalence point, right? The equivalence point is where the amount of reactants are stoichiometrically equivalent, all right? So you have the same number of moles of both reactants in this particular case, right? So what's the next step? Well, the next step is that we need to find the concentration of what is left there. So the concentration of NaA, which by the way would be the same thing as the concentration of A minus, is equal to the moles of NaA, which is 6.00 times 10 to the minus 4 moles, divided by the volume. Now, what's the volume? The volume would be the total of the 6 mils of the butanoic acid, and if I remember correctly, the 12 mils of the sodium hydroxide, right? In fact, let me just confirm that to be the case. I don't want to make any wrong assumptions. Right, 12 mils, okay. So that would be, whoops, let me scroll down a bit. So this would be 6.0 mils plus 12.00 mils. And then we have to convert that to liters. So I'm going to put here as a conversion factor, 1 liter over 1,000 mils. And let's see what that gives. So 6 times 10 to the minus 4 divided by 18, which is 6.0 plus 12. 1,000. Okay, so according to my calculation, this works out to be 0.0333 M. All right. Now the A minus itself will act as a base with water, right? So you're going to have this hydrolysis reaction taking place. All right. So initially at this stage, the molarity of the A minus would be the 0.033. Don't need to worry about the water. We don't know. Well, that will be 0 and that will be 0 initially. And again, I'm going to need some more space. So let me erase down here. Okay, so we don't know what the change is because it's a weak base, but we know that we can call that minus X for the A minus, which means that over here, it's going to be plus X and plus X, right? So the equilibrium situation would be you're going to have 0.0333 minus X. Here you're going to have X, here you're going to have X. So we can write down a KB expression for this, which would be equal to the concentration of HA times the concentration of OH minus all over the concentration of A minus. And then we plug the numbers in or the terms in. We're going to end up with X squared over 0.0333 minus X. Now, again, this is one of those situations where you won't be given the KB for the conjugate base, but we know that the Ka for the acid is this, right? So we can write down an expression for Kb, which will be equal to Kw divided by Ka. So Kw is 1.00 times 10 to the minus 14, and Ka is 1.52 times 10 to the minus 5, right? So that would be equal to 1 times 10 to the minus 14 divided by 1.52 times 10 to the minus 5. So according to my calculation, this works out to be 6.58 times 10 to the minus 10. And that would be equal to X squared over 0.0333 minus X. So basically, we go through the same steps as we did in previous problems. We assume that X is much less than 0.0333. And again, I'm limited with space, so let me erase what's up here. Okay, so if we make that assumption that X is small compared to 0.0333, then this equation simplifies to X squared over 0.0333 is equal to the KB, which is 6.58 times 10 to the minus 10, which means that X would be equal to the square root of 0.0333 times 6.58 times 10 to the minus 10. And let's see what that gives. So that would be 6.58 times 10 to the minus 10 times 0.0333 and find the square root. So according to my calculation, this works out to be equal to 4.68 times 10 to the minus 6. And again, as always, we find the percent dissociation, which I'm quite sure in this case is going to be less than 5%. 4.68 times 10 to the minus 6 divided by 0.0333 times 100% m. So divided by 0.0333 times 100%. So this gives 0.0141%, obviously less than 5%. So therefore, the assumption that we made down here is valid, right? And therefore, as a result, we can calculate the POH, because the POH comes from the concentration of OH minus, which is X right here. So concentration of OH minus, therefore, is equal to 4.68 times 10 to the minus 6m, which means that POH is equal to minus log of 4.68 times 10 to the minus 6. So 4.68 times 10 to the minus 6 log. So that would be equal to 5.33, which means that the pH is equal to 14.00 minus 5.33. And according to my calculation, that works out to be equal to 8.67. And that's how that is done. All right. I must apologize for the jumbled look, but that's because I'm lacking in space, so I have to keep on erasing different parts to continue to answer the question. All right, any questions about this? Any questions? Okay. Let me clear this. 1 minute here. Okay, let me clear this. And scroll down. Oh, that's it for number 2. Okay. So let's look at number 3. Now, number 3 is dealing with a concept known as solubility product. And this basically, this term, the solubility product, applies to sparingly soluble ionic compounds. So applies to sparingly soluble ionic compounds. Okay, so what we're talking about here are basically ionic compounds that we normally consider to be not soluble in water. In truth and in fact, every compound, including ionic compounds, have different, what's the word I'm looking for? Different levels of solubility. Some compounds are very soluble, like sodium chloride, and then you have some compounds like silver chloride, where only a small fraction of the solid will actually go into solution. If you add solid silver chloride to water, only a small fraction, very, very minute fraction of the silver chloride will go into solution. So we're talking about those kinds of compounds. And basically, what you'll find is, and I'm going to use this example here, this question as an example. So this is silver acetate, silver 1 acetate, right? So basically, when silver acetate is added to water, so you add some of it to water and you stir it, try to make it dissolve, only a small fraction will go into solution. So therefore, you're going to have eventually an equilibrium between the silver acetate and the silver and acetate ions on the right side of this equation, right? And we can write down an equilibrium expression for this, in which case this would be KSP, right? That's equilibrium constant for this system. And that would be equal to the concentration of Ag plus times the concentration of C2H3O2 minus, right? Now, please note that these ions are in an aqueous solution, and the solid here would be in a solid state, right? So because this is a solid, it does not appear in the equation. And I remember talking about this earlier when we were talking about equilibrium. I remember saying that solids and liquids do not appear in any equilibrium expression, right? The only terms that will exist in an equilibrium expression would be aqueous solutions and gases, all right? Okay, so that's basically just some introductory stuff I need to say concerning the solubility product, right? And let me just say also that solubility product values are very low. In fact, there's a table that I have made available to you guys. Let me see if I can show you what it looks like, which gives you the solubility product of different compounds. So if you go to tables, and then you go to where it says solubility product, constants, and okay, let me just get rid of this so you can see this more clearly. Let me download this here. Okay, so this is a table which gives a list of ionic compounds, sparingly soluble ionic compounds, and their KSB values, right? And if you look at all these numbers here, for all these different compounds, you see that they're very low. 3 times 10 to the minus 34. 9.84 times 10 to the minus 21. I think the highest value I've seen here so far is 2.55 times 10 to the minus 4, and that is even small. Actually, this is even larger, 4.64 times 10 to the minus 3. But most of these numbers here are very small, right? Which is typical of ionic product values. Excuse me, solubility product value, that's what I meant to say, right? So it's not unusual for you to have a KSP value that is very small. That's to be expected because the concentration of ions in these solutions are very small, all right? Okay, so this table, of course, you'll have access to when it comes to your tests, final exam, and so on, all right? I'll make sure that that's available to you. Okay, so going back to the question. Here. So, as I said before, this is the equilibrium system that we're dealing with. Oh, come on. Okay, so it is Ag C2H3O2 to form Ag plus C2H3O2 minus. All right, so the question is asking for the concentration of this particular solution of silver acetate, right? So again, we set up a nice table. Oh, and let me say again, this is solid, this is aqueous, this is aqueous, all right? So we set up a nice table. In this ice table, you don't need to concern ourselves with the solid concentration. So the question is, what is the concentration of Ag plus and the acetate? I'm just going to say S is going to be the solubility of the compound, right? I'm going to let S be the solubility of the compound. So if I do that, that means that if S is the solubility of this, that means that the concentration of Ag plus will be S and the concentration of acetate will be S. But I just realized I made a mistake. Initially, you'd have none of these. I'm sorry about that. So let me correct myself here. This will be 0, this will be change. If S is the solubility, then the change in concentration of the silver is going to be plus S, and the change in the acetate concentration is plus S. So at equilibrium, you're going to have S and S here, and therefore we can write down the KSP expression. The solubility product is equal to the concentration of Ag plus times the concentration of C2H3O2 minus, right? And then we put in the terms S here and S here, so that will be equal to S squared, which means that S would be equal to the square root of KSP, and they gave us the KSP value, which is 1.94 times 10 to the minus 3. And that's it. All we have to do is find this out. So 1.94 times 10 to the minus 3, square root. And according to my calculations, this works out to be equal to 0.0440 M. So that would be the concentration, the molar concentration of the silver acetate. All right? Okay, any questions about this? Any questions? Any questions? Any questions? Okay. Let me clear this here. Now, in the case of question number 4, they're asking for the same thing, but it's a different compound. And because the compound is different, the approach is slightly different. So let me explain what we mean by that. So again, I'm going to write down the equation for the dissociation of the lead to chloride. So PbCl2 will dissociate to form Pb2 plus and 2Cl minus, right? Initially, we're going to have none of this, but the change here, again, assuming that S is the solubility of the compound, that means that the change here for the lead 2 plus is going to be plus S, and for the chloride would be plus 2S, all right? So at equilibrium, you're going to have S here and S here. I'm sorry, 2S here. So therefore, we can write down the KSP expression. Now, what's the KSP expression in this case? It's going to be the concentration of Pb2 plus times the concentration of Cl minus squared, right? And then we put in S where this is, 2S where this is, 2S squared, and then this becomes 4S cubed. So therefore, KSP in this case would be equal to 4S cubed. So therefore, S would be equal to the cube root of KSP divided by 4. So the cube root of KSP, which is 1.17, times 10 to the minus 5 divided by 4. So let's see what that gives. 1.17 times 10 to the minus 5 divided by 4. And then find the cube root of that, which is that. Okay, so according to my calculations, this works out to be equal to 0.0143 M. And that's how that is done. Okay, any questions about this one? Any questions? Any questions? Any questions? All right, let me clear this and scroll down. Okay, now this one is a hypothetical situation here. You have a compound where the formula is A2B, right? Now the assumption is that A would be the positive ion, the cation, and the B would be the anion. That's the assumption that we have to make, right? And it says that the saturated solution of A2B has a concentration of 4.35 times 10 to the minus 4. What is the solubility product constant? Okay, so in this case, what I'm going to do is write down the dissociation for A2B. So assuming that A is the positive ion, I'm going to end up with 2A plus B2 minus. Right? Now, again, I'm going to set up an ice table. Initially, I would have none of this, none of this. The change here, now the question says that the concentration of the saturated solution is 4.35 times 10 to the minus 4. So that would be the solubility. Solubility would be equal to 4.35 times 10 to the minus 4, right? So if that's the case, that means that as far as the A plus is concerned, the concentration would be, the change would be plus 2S, and the change for the B2 minus would be plus S. So at equilibrium, you're going to have 2S and then S here. So that means that KSP would be equal to 2S squared. In fact, let me go do it stepwise so that you can follow clearly. The KSP expression is going to be concentration of A plus squared times the concentration of B2 minus. And then we put in the terms. For A plus, that would be 2S, and we square that. And then for the B2 minus, that would be S right here. So therefore, this would be 4S cubed, which is equal to the KSP. So therefore, S would be equal to the cube root of KSP. Oh, I'm sorry. We're finding the KSP, not S, because S is given. So therefore, KSP is equal to 4 times S cubed. S is equal to 4.35 times 10 to the minus 4 cubed. And that's it. So let's see what this gives. 4.35 times 10 to the minus 4. Then we do the cube thing. And then we multiply by 4. And according to my calculation, this works out to be equal to 3.29 times 10 to the minus 10. And that's it. All right? Any questions about this one? Any questions? Okay, let me clear this. Scroll down. Okay, now here's an interesting question. It says the solubility product constants are usually specified at 25 degrees. And that is true. If you look at the table that I showed you earlier, they give you this at 25 degrees, right? So whenever you look up the KSP value, you can assume that the temperature is 25 degrees. So the question is asking, how does the KSP value for a chemical compound depend on temperature? So let me hear your ideas as to the answer to this question. How do you expect the temperature to affect the KSP value? Any ideas? What what would you expect to happen to the solubility of a compound, an ionic compound, when you increase the temperature?
Becomes more soluble.
Okay, good. Okay, very good. That's what I would expect too, right? So if the compound becomes more soluble, then what happens to the Ksp value? Now remember, the Ksp the Ksp would be equal to the product of the concentration of the ion. So let's say it's silver chloride, right? This is what Ksp is equal to. So if the solubility increases, then what would you expect to happen to the Ksp value?
Increases also.
Exactly, right? So yes, the Ksp would increase. Ksp will increase with increasing temperature. And that is true in most cases. There are some exceptions to this, but in the vast majority of cases, that is indeed the case, right? So let me just erase this here, right? Ksp will increase with increasing temperature, all right? Okay, very good. Let me clear this here. Okay, the next question is asking for you to calculate the molar solubility of lead to chromate. So, again, I would write down the equation for the dissociation of lead to chromate, like this, Pb2 plus CrO4 2 minus. And initially, you'd have none of these. The change here would be in the case of the lead 2 plus S and plus S here, right? So at equilibrium, you're going to have S and S, which means that Ksp is equal to the concentration of Pb2 plus times the concentration of chromate, which would be equal to S times S, which is S squared, which means that S is equal to the square root of the Ksp, which is equal to the square root of 1.8 times 10 to the minus 14. And then I find the square root of that. And according to my calculations, this works out to be equal to 1.3 times 10 to the minus 7 m. So that would be the answer in the case of 7A. All right? Okay, any questions about this one? Any questions? Now, in the case of the B part for number 7, clear this. It's based on, in part, what was done in A, or the information provided in A, because in this case, now, what you're trying to do is dissolve the lead 2 chromate in a solution which already has sodium chromate, all right? Now, sodium chromate will dissociate. Oh, somebody has a question? Oh, I'm sorry, Mr. Renly, I just saw your response to the question I asked earlier. Okay, so, but you're correct, of course. Okay, what was I saying? Okay, so what I would do first in answer to this question is to write down the equation for the dissociation of the sodium chromate. So Na2CrO4 will dissociate completely, right? And we know that to be true because all sodium salts will undergo complete dissociation, right? So you're going to end up with 2Na plus CrO4 2 minus, right? So basically, you're going to have a lot of chromate ion present in the solution before you add your lead 2 chromate. So when the lead 2 chromate is added, this is the dissociation that is going to occur. All right. Now, in setting up our ice table, the initial concentration of the lead 2 plus is going to be 0. But the initial concentration of the chromate ion is going to be 0.020. And the reason why is because this chromate here comes from the sodium chromate, and the molarity of that sodium chromate is 0.020, right? So that's one difference between the previous question and this one, because now we're initially having a concentration of 0.020 m, right? The change here, if S is the solubility of the lead 2 chromate, is going to be plus S here and plus S here, right? So at equilibrium, you're going to have S, and here you're going to have 0.020 plus S. Now, because we're dealing with something that is sparingly soluble, we can basically assume that S is much less than 0.020, which means that this here simplifies to 0.020, right? And therefore, we can write down that KSP is equal to S, which is the concentration of the lead 2 plus, times 0.020, and therefore we can solve for S, which is KSP divided by 0.020, and the KSP was, what was the KSP? 1.8 times 10 to the minus 14. So 1.8 times 10 to the minus 14 divided by 0.020. And let's see what that gives. Okay, so according to my calculation, this works out to be equal to 9.0 times 10 to the minus 13 m, right? And that's the answer for the B part. And this is an example of what we call the common ion effect. The common ion effect, right? And basically the common ion effect is the, what's the word I'm looking for? The suppression of the dissociation of an ionic compound due to the presence of a common ion. All right? So basically what we're saying here is that because this ion is present, the chromate ion was present before we add the water, that reduces the solubility of the lead 2 chromate. So the solubility of lead 2 chromate in this solution is 9.0 times 10 to the minus 13. Can somebody remind me, what was the solubility that we calculated in the A part?
1.3 times 10 to the negative 7.
Right, okay, so you can see the difference here and here, right? In pure water, the solubility of the lead 2 chromate is 1.3 times 10 to the minus 7. In the case of a solution of lead 2 chromate, where the molarity is 0.020, the solubility is 9.0 times 10 to the minus 13. So basically the presence of the chromate ion reduces the solubility of the lead 2 chromate. And we can explain that using Le Chatelier's principle. Excuse me. Basically what Le Chatelier's principle would predict is that because of the high concentration of that, it will push the equilibrium to the left and thereby reduce the solubility of the lead 2 chromate. All right? Okay. Any questions about that one? Any questions? Okay. Let me clear this. And let's scroll down. Okay. Now this question has to do with indicators, right? And you may have met in previous, especially in lab courses, or in this lab course, well, Chem 1 lab or Chem 2 labs, you would have met indicators for acid-base reactions, right? Basically, an acid-base indicator is a substance. In fact, let me write it here. It's either a weak acid or base whose color is dependent on the pH of its environment. all right? So in one environment where the pH is high, the indicator will take on a particular color. If the pH is low, then the indicator will take on a different color, all right? So that's basically what an indicator is, all right? And let me just briefly explain how an indicator works. Let me come down here and click on this. Okay, so let's say, and I'm just going, this is just purely a made up hypothetical example. Let's say you have an indicator H, whoops. Okay, so let's say you have an indicator H, HA, right? And it's added to water, and therefore you have this equilibrium H plus A minus, all right? So let's say the color of this, this is just a made up example, as I said before. So let's say the color of this is blue, right? And let's say the color of this is, I don't know, yellow, all right? So if you have more of this present compared to this, then the overall solution will be blue. If you have more blue molecules compared to the yellow conjugate base, then the solution will be blue. If the reverse is true, if you have more anions present, A minus, compared to HA, then the solution will be yellow, right? So you can actually push the equilibrium one way or the other by adding the appropriate acid or base. So if, let's say, you add a base, OH minus, right? Then the concentration of H plus will decrease because the OH minus will be reacting with the H plus. The concentration will decrease, which means that the equilibrium will shift to the right, right? And therefore, the concentration of A minus will increase, all right? And therefore, the solution will appear more yellow, okay? On the other hand, if you add H plus ions, then the concentration of H plus will increase and the equilibrium will shift to the left, right? Which means that the concentration of HA would increase, which means that the solution will become more blue, all right? So that's basically how an indicator behaves, all right? It depends on which one is in greater amount in terms of the concentrations, and the one that is in greater amount, either the acid or the conjugate base, will determine the overall color of the solution. Okay, so with that said, let's go to the question. It says that, well, actually, it's using the same colors that I mentioned before. It says that this indicator, HIND, is yellow in 0.1 molar sodium hydroxide and blue in 0.1 molar HCl. And it says the pH range in which a color change occurs is in the range of 3.6 to 5.2, all right? Okay, where is this thing here? Okay, so please note it's yellow in base and blue in acid. And this is a pH range where the color change would occur, all right? So the first question is for you to write down the equilibrium equation. And that equation would be HIND to form H plus IND minus, all right? So that's the first, the answer to the A part. Now the question is asking, what color is HIND? So let me hear your response to that question. What do you think the color of the undissociated molecule is?
Blue?
Exactly. Can you explain why?
Because it has the H plus ion attached to it.
Okay, because it's blue in hydrochloric acid, right? So
Right, yeah.
basically the concentration of H plus will be high, which means that it's going to push the equilibrium in that direction, right? So therefore that means that the color of the HIND must be blue. And that's the answer here, all right? And that, of course, by default, you should be able to tell me what the answer for what is the color of IND minus.
Yellow.
Yellow, exactly. Okay, very good. Now the question here in C is asking, what is the pH at the transition point for this indicator? So the transition point is where the color change over from, in this case, blue to yellow or yellow to blue, depending on which end you're starting from. So what would be the pH at this transition point? And the hint lies right here. So what do you think the pH at the transition point is? Well,
Is it just that whole range?
nope. Remember, the range that is given is a range over which a color change is taking place, right? So below 3.6, the color is going to be blue, and above 5.2, the color is going to be yellow. What the question is asking is more specific. The question is asking the pH at which the transition takes place. So the question is not asking for the range, it's asking for the actual pH where you're going to have the changeover from one color to the other.
Would it be the middle of the range?
Okay, I'm hearing a very faint voice. And if I hear you correctly, you're saying that it's in the middle of the range?
Yes,
Exactly. And what's that middle?
4.4.
4.4 is indeed correct. All right, very good. Okay, moving along. In fact, let me clear this first. Moving along to the D part. What is the value of pKa for this indicator? Very interesting question. What is the value of pKa for this indicator? Maybe I should give you a little hint. Remember, Ka is equal to, in this case, the concentration of H plus times the concentration of IND minus over the concentration of HIND. Right? And let me see here. Oh, okay. For those of you enrolled in my lab, we did one experiment where we set these two to be equal to each other, the concentration of IND minus and the concentration of HIND. When these two are equal, they will cancel out, which means that Ka is equal to concentration of H plus, right? So, and remember I said in answer to this question that the answer for the pH at the transition point is 4.4. That's a point where these two are equal to each other, right? So if the pH is equal to 4.4, what is a pKa? Okay, somebody is saying something in the chat. Nope. Mr. David is saying minus log of 4.4. That would not be correct. Can anybody else take a stab at this?
Is it 4.4 equals negative log of the concentration of H plus?
Exactly. Which is the pH. And therefore, if we find a minus log of both sides, this is pH, and this would be the pKa. So the pKa would be equal to 4.4. all right? Because the pH is the point at which you have the concentration of the conjugate base and the acid equal to each other, which means that the Ka is equal to the concentration of H plus, which means that the pH will be equal to pKa, which is 4.4. Okay, next question is, what is the Ka of this indicator? What is the Ka of this indicator? If pKa is equal to 4.4, then what is Ka equal to?
Could you explain the difference between what the pK, like what is pKa and what is Ka?
Okay, so the relationship between pKa and Ka is this. pKa is minus log of Ka, right? Now, if you want to find Ka and you're given the pKa, then Ka is equal to 10 to the minus pKa, right? So to answer this question, what is a Ka, right? That would be 10 to the minus pKa, which is 4.4, which is equal to okay, so according to my calculation, 4 times 10 to the minus 5. That would be the Ka value.
But
Okay,
could you
any
explain
questions on this one?
like what actually is it though? Like that's okay, pKa is equal to that, but like what is the pKa compared?
Okay, the
You know what I'm saying?
pKa is another way of expressing the strength of an acid. You can use Ka, but you can also use pKa. People use one or the other depending on, you know, what they're trying to work with. So the Ka, if you remember, the larger the Ka value for an acid, the stronger that acid is, right? But the lower the pKa value, the stronger the acid is. All
Okay,
right?
so they're kind of just the inverse of each other.
Kind of, yeah. Okay. F. It says at pH 2.2. Oh, so now they're asking for the color of the solution when the pH is 2.2 and whether or not the acid molecule is, its concentration is greater, less than, or equal to the concentration of IND minus, the conjugate base, right? Now, the key thing you need to remember is that the transition point here is 4.4, right? So what that tells us is that if the pH is less than 4.4, that means that the color of the indicator, what was the color again? The color of the indicator will be blue if the pH is less than 4.4. And if the pH is above 4.4, then the indicator color would be yellow. All right. So let's see here. Let me get this in the right place. Okay. So what would you expect the color to be in the case of pH 2.2?
Blue.
Blue.
Yes.
Okay. So therefore, that means that the concentration of HIND is it greater, less than, or equal to the concentration of IND minus?
Greater than.
Greater than. Okay, very good. All right. At pH 7.0, what's the color of the indicator?
Yellow.
Yellow. And is the concentration of HIND greater than, less than, or equal to the concentration of IND minus?
Less than.
Less than. Okay, very good. At pH 11.3, this indicator is the color what?
Still yellow.
Okay. And therefore, is the HIND concentration greater than, less than, or equal to IND minus?
Less.
Less than. Okay, very good. All right, let me clear this here. And scroll down. Okay. Now, when we get to pH 4.4, right? What would you expect the color to be? Now remember, pH 4.4 is the transition pH. So that means that you expect to have an equal amount of both IND minus and HI minus. I'm sorry, IND minus and HIND. So what say you is the color of this solution?
Would it just be like a mixture of blue and yellow?
Yeah, so what would that
Like
color be?
green?
Exactly. So green. And HIND would be what?
Equal.
Equal to IND minus. Okay, very good. Now, here it says at pH 4.3, what is the indicator color? Now, remember, I need to scroll up to show you this here. Remember I said that the color change occurs in this range, right? So what that means is that you're going to have a relatively high number of green relative to the blue molecules or vice versa, right? So 4.3 lies within that range. So going back to the question. What would you expect the color here to be?
Would it be like a bluish green?
I would stick to green. And what would be the concentration of IHND relative to IND minuses?
Greater than?
Hmm?
Greater than?
Yeah, greater. So, right. Okay. Now in this case here, it says you have a solution where the concentration, an acid solution, nitric acid, its concentration is 0.001 m. And it's asking for the color of the indicator in the solution. Now, let me give you a little hint here. This here is the same thing as 10 to the minus 2m, which means that the pH is equal to 2. So what would you expect the color of this solution to be? Of the indicator in this solution to be? Oh, somebody has a question. Okay, I'm not sure what question you were answering to Mr. David. Sorry about that. Or are you answering this question? Oh, okay, good. All right. So yes, the answer is blue. All right. And what do we put here? Is the HIND greater, less than, or equal to IND minus? Okay, let's see. Somebody's saying something in the chat. Yes, you're right. Greater. So greater would be here. Okay, very good. And then in this case here, it's 0.001 m potassium hydroxide, which is 10 to the minus 2 m, the pH of this is going to be 12. All right? So what would be the color of this solution?
No, it's 12 because you have to do the 14 minus 2 for that
Exactly,
one, right?
right.
Okay.
Mhm. Okay, somebody said something in the chat, 2 persons actually. Yellow, yellow, both persons are correct. So let me put yellow here. And what would go here?
Less than,
I'm sorry?
less than.
Yes, you're absolutely right. Yes, less than. Okay, very good. Let me see here, what next? Okay, I'm not sure we'll have enough time to complete this one. Let me see here. Yeah, I don't think I'll be able to complete this one. Just scroll down here. Okay, I'm gonna leave the last 2 for next week. All right. Because these are a bit involved in terms of finding the solution to these problems. All right. Okay. So in the time that's left, let me remind you of the test that is in the testing center. Right. It should be there. Make sure that you check the correct number of pages. Make sure that the front page says spring 2026, and also make sure that they give you the tables, including the table. This table right here, I'm about to show you. Dissociation constants. Right? So this table you should be given, right? I've left instructions for that table to be given in addition to the periodic table and the other tables that you're familiar with, all right? So you have until Friday to do it. If there are any issues, right, please contact me, all right? In fact, I would suggest that if you're not given all the materials and so on, then don't do the test, because it's not fair to you to do it without the requisite information that you need, all right? And then come and see me, and then we can talk about you making up that test. Okay, somebody's saying something. Is it possible that you could publish past test number 2 key? Let me see. Let me see. Test number 2. Okay, test keys. Oh, I'm sorry. That's not it. Past test answer keys. That's what I'm looking for. Well, this should be a good, let me see here. Okay, so that's test number 1. Okay, test number 2. Yeah, test number 2 that I'm showing you here, that should prepare you. Let me see here, test number 3. Right, I wouldn't look at test number 3 here. Yeah, so I would use test number 2 here as, for review of to prepare for your test number 2. Somebody's asking another question. There are no more appointment time slots for the Ocala campus until next week. Okay, well, should I book it for Levy or Citrus campus? Yes, if it's not inconvenient for you, yes, I would do that. All right. Okay, any other questions concerning the test? I would say also that you should not only limit yourself to reviewing your assignments and your past test keys, but you could also look at your textbook questions as well, right? The more practice you get in, the better you become at solving these problems, all right? Okay, if there are no other questions, that's pretty much it for today. before I forget, let me, oh, somebody has another question. Did we take roll? Yes, I did take roll. Let me see, Mr. Ranley, if I got you down. Ranley. Yes, I got you down. All right. Okay, before I forget, let me also, in the module section, publish the videos for the next chapter, which is thermodynamics. So it's a relatively short chapter. So make sure you watch those videos and come prepared to work some problems in that chapter, all right? So that's pretty much it for today. So I'll see you guys next week.
Just confirming it's assignment 3 and 4 are what's on this test, right?
Yes, assignments 3 and 4, yes, sir.
Okay, thank you.
All right, any other questions in the remaining 4 minutes?
I just had a quick question about the table that you showed us. What were the Ka2 and Ka3 values that were on there?
Okay, so that's for acids that can release more than one proton, right? So for the release of the first hydrogen ion, the Ka1 value would be for that release. And then for the second hydrogen ion, that would be Ka2 and Ka3 for the third hydrogen ion.
Okay. Is that,
Right.
are we gonna need to use that for the exam? Is there gonna be any examples with
It
that?
depends. It depends on the question. If the question involves an acid that can release more than one hydrogen ion, then yes, the Ka1 and Ka2 and if needed Ka3 values would become useful. We did one example. I think there's one question in the assignments which deals with that situation.
Okay, thank you.
You may want to review that. Okay, 3 minutes remaining. Any more questions? Okay, somebody had a question in the chat. Oh, yes. And I must apologize for not turning up. I had an awful illness, especially my throat. I don't know, it was hurting so bad. So I apologize for not showing up when I should have. But yes, you can come to today's lab and finish up on, if I'm not mistaken, it's the colligative properties, right? Okay, good, right. So yeah, you can come at 9:30. Okay, 2 minutes. Any more questions? 2 minutes.
Thank you. See you next week.